So we've now worked with homogeneous equations quite a bit for linears, and so we're now going to work into the general solution of a linear non-homogeneous equation. And what we're talking about here is when that right-hand side of the equation is not equal to 0. So what we've got is that y double prime, so we're in standard form, y double prime plus some function p times y prime plus some function q times y equals some function g, where p, q, and g are all continuous on my interval a to b. And so what we say is if that u and v are two solutions, then u prime plus pu prime, or u double prime plus pu prime plus qu equals g must be true, and v double prime plus pv prime plus qv must equal g as well must be true. So if we were to subtract these two equations, let's just say that they were both solutions and subtract them, we'd have u prime minus v, or u double prime minus v double prime, plus that function p times u prime minus v prime, plus that function q times u minus v, would equal g minus g, or 0. So we've given ourselves a homogeneous equation where u minus v is the solution of that homogeneous equation, y double prime plus p y prime plus qy equals 0. If we then let our particular solution, so as opposed to our complementary solution, which we're going to talk about here in a second, if we let y sub p be a particular solution of that original y double prime plus py prime plus qy equals g, our linear non-homogeneous equation, if we let y sub p equal the particular solution of that, and y be any solution of that as well, then I know that y minus yp, or y minus y sub p, excuse me, is now a solution of our homogeneous equation. And y1, y2 is an f-sauce for that homogeneous equation. So what we get is this y minus our particular solution is of that form c1y1 plus c2y2. That should look familiar to you. When we subtract our yp, or add our yp, excuse me, we get that c1y1 plus c2y2 plus some particular solution. So what we're getting at is that this is the general solution for a non-homogeneous differential equation that's linear. It equals the general solution of our homogeneous plus some particular solution of the non-homogeneous. What we call that general solution of the homogeneous, we call that the complementary solution. So from now on, we're going to denote that y sub c and continue to denote the particular solution portion as y sub p. And we'll look more at that particular solution part. We'll look more at that guy in 3.8 and 3.9. So let's take a look at an example. If I asked you to verify that the particular solution 3t minus 4 was a solution of y double prime minus y prime minus 2y equals 5 minus 6t, where p is negative 1, q is negative 2, and g is 5 minus 6t, and then also use the fact that y of 0 equals 3 and y prime of 0 equals 11 to solve the IVP, we'd go through the following process. The first thing we'd do is verify that that 3t minus 4 is in fact a solution. So the first thing we want to do is find y sub p prime and y sub p double prime. So we find y sub p prime to be 3 and y sub p double prime to be 0. We then take those values and plug them in to our differential equation. So we plugged in 0 for y double prime, 3 for y prime, and then we had the negative 2 times my original y sub p, set it all equal to g. I then evaluate the left side and make sure that, yep, sure enough, 5 minus 6t does in fact equal 5 minus 6t. So then I move into the complementary solution. To find my complementary solution, I'm basically saying, look at this left side of the function and pretend it equals 0 to find that complementary. So my coefficient of lambda squared is going to be 1 because my coefficient here was 1. My coefficient of lambda is going to be negative 1, and my c is going to be negative 2 because that was my coefficient here. I set that equal to 0. I solve for lambda. I get lambda values of 2 and negative 1. This gives me the two solutions, e to the negative 1t and e to the 2t. So I set up my complementary solution. My complementary solution now is C1 e to the negative t plus C2 e to the 2t. There's my complementary solution portion. Plus 3t minus 4. Where did I get this? That was the particular solution that I was given. Remember, it's yc, which is this whole chunk right here, plus yp, which is this chunk. So we're verifying that it is in fact a solution. Oh, we already verified this. We're actually setting up our IVP. Sorry. So now we're coming down here. We've got our general solution. We find our general solution's derivative, so y prime, and then we plug in our initial values. So my y prime was negative c1 e to the negative t plus 2c2 e to the 2t plus 3. And so now I plug in those initial values, which were y of 0 equals 3 and y prime of 0 equals 11. So I come down to where I plug those in, and I've got 3 equals c1 plus c2 minus 4, and 11 equals negative c1 plus 2c2 plus 3. These just come from plugging in my initial values. Now I go ahead and solve. I get a c2 of 5 and a c1 of 2. So to establish my final solution for this IVP, I get a y of t equals c1 of 2 times e to the negative t plus c2 of 5 times e to the 2t plus my particular solution, 3t minus 4. This extra part is a product of the fact that this is a non-homogeneous differential equation. Now we're going to get into talking about superposition of particular solutions. This does not apply to non-homogeneous, but basically if U1 and U2, are two solutions of the differential equation y double prime plus py prime plus qy equals g. That's a non-homogeneous, where g is non-zero. Then that u1 plus u2 is not a solution. I can't take two functions, add them, and call it a solution of this differential equation. If we did do that, we would get that u1 plus u2, we're calling it w for sake of condensing it, I guess. So we get w double prime plus pw prime plus qw equals g plus g when we add those two functions together, or in other words, 2g. And there's no way that that could give us a solution because we've got a 2g instead of a 0 over here. So what we do is we get a different form of superposition, and here's where we arrive at Theorem 3.4. Theorem 3.4 says, if U is a solution of y double prime plus py prime plus qy equals g1 on the interval a to b, and on the same interval, v is a solution of the same differential equation with a different g, so the right-hand sides are different, and a1 and a2 are any constants, then my particular solution is the constant times u plus the second constant times v. That is a particular solution of the combined differential equation where a1 and a2 multiply by those g functions. The proof is in exercise 13, so if you'd like to do the proof, you're more than welcome to do